All right. So we're going to continue our discussion on radiative transfer, and we're going to kind of use some of the concepts which we learned. So we learned the vocabulary. How do we account for radiation? How do we do the accounting? And so we're going to use that now to figure out what happens when you have a medium where radiation is propagating, and the medium can either absorb the radiation or emit extra radiation. So if you remember, we left off last video by saying that the specific intensity along a ray is always constant. It never changes as long as there's no absorption or emission, right? So now we're going to say what happens if there is absorption or emission. Of course, the specific intensity is going to change. It's going to decrease if there is absorption. It's going to increase if there is emission. And we're going to talk about how we do the accounting for that. How do we take care of that quantitatively? Okay, so let's start with absorption of radiation. The most important thing to know about absorption is that it is a multiplicative effect. Okay, so I say it in the sense that it's not additive. You don't add something to the radiation, you take away a fraction of the radiation, and that is absorption. So you don't add or subtract a set amount, you actually take away a set fraction, not a set amount. So it's a multiplicative effect. And the easiest way to think about absorption is to think about it very mechanically in terms of small spheres which are absorbing radiation. And it's very helpful to have this picture. So I've drawn that picture here. I have a differential volume element here of length ds and cross-sectional area dA. So it's a cylindrical element. And I say it's a differential volume element or an infinitesimal volume element, in that it's small enough that the internal angles within this system are not important. So you can think of it as the volume element which is actually axially surrounding a single ray which is passing by, shown by this dotted line. Okay, so now question we want to ask is, let's say I1 is the specific intensity entering this volume, I2 is the specific intensity leaving this volume. How do you relate I1 to I2 based on the properties of the material in this volume? So how do you account for absorption? So an obvious statement you can make is I2 is equal to I1 times the fraction of radiation that is not intercepted by particles in that volume, right? And that is just axiomatically true. But how do you actually calculate this? So imagine that these absorbing things are basically tiny spheres, okay? So it's just a conceptual picture. So imagine they're tiny spheres. Any radiation falling on one of the spheres is lost completely. It never makes it out of the cylinder. Any radiation that doesn't intercept a sphere just makes it out of the cylinder. And so now it just becomes quite simple. If you want to know the fraction of radiation intercepted, it's basically the total cross-sectional area of all of these spheres divided by dA. So it's the fractional cross-sectional area which is covered by these spheres. So let's say the volume density is N and the individual cross-sectional area of a sphere is sigma. So N times dA times ds is basically volume density times volume. So that's the total number of particles here. So N times dA times ds times sigma is the total combined cross-sectional area of all of these particles. So N times dA times ds times sigma divided by dA is the total cross-sectional area divided by the total area of the cylinder. So that basically gives you the fraction of radiation that is going to be intercepted. Okay, so that fraction is just the total cross-sectional area of things that are absorbing divided by the total cross-sectional area of the cylinder. So that's what I've written here. So I've said I2 equal to I1 times, notice the second fraction here, N times sigma times dA times ds. That's the total cross-sectional area in the numerator divided by, total cross-sectional area of all the little spheres divided by dA. So this fraction is the fraction of radiation that is intercepted. And so this whole thing here is the fraction of radiation that makes it out. So it's kind of 1 minus the fraction which is intercepted. And so that works out to be 1 minus N times sigma times L. Let's check that if this makes sense. If N is large, then there are a lot of absorbers. Make sure not much escapes. If sigma is large, again, the cross-sectional area is large, so not much is going to escape. If L is large, then of course, you have more absorbers, you go through more path length, and so more is going to get absorbed. So let's write what the fractional change here is. So I'm going to bring I1 to the other side. So I2 minus I1 by I1. So this is the fractional change in specific intensity is equal to minus n sigma times ds. You can now take limits and write it as a very simple differential equation. And it has a pretty obvious solution. So you immediately see that if there is absorption, then the specific intensity goes down exponentially. Okay, so this is the nature, this is the common solution for any process where the amount of reduction is fractional. Okay, so any process where the amount of reduction is fractional, you're going to end up getting this. Okay, so let's talk about emission of radiation. Okay, so emission is different from absorption in that emission is an additive effect, which means that the particles in this medium are emitting, they're doing their own thing. They don't really care how much radiation comes in or comes out, or if there is any radiation at all, they're just going to emit independently. Okay, so technically you would say this is spontaneous emission. They're going to just emit spontaneously. It doesn't matter what how much specific intensity is coming in or going out. So it's just an additive effect. Whatever is coming in, you're going to just add something to it. And so it's very easy to write an equation for emission once you define something called the emission coefficient, which is epsilon. So epsilon is like is kind of similar to specific intensity, but it's per unit volume instead of cross-sectional area. So epsilon is the total amount of energy emitted per unit volume, per unit time, per unit frequency, and per unit solid angle. So notice that it's very similar to I1, but I1 has per unit square centimeter, so per unit area, but E is basically per unit volume. Okay, so let's assume how much of that energy is going to add to this ray, which is going across the cylinder. Okay, so in this case, we are following the transfer of radiation along a single ray. So we don't really care about emission that goes out of the cylinder here or goes out this way. We're only talking about emission that adds to that particular ray. Okay, so I2 is I1, whatever is coming in, plus epsilon times dA times ds is basically, dA times ds is the total volume. So this is basically the amount of emission in the entire volume. And we are working with specific intensities. So we want to know along this ray, what is the amount of energy that is added per unit area, right? So specific intensity is energy per unit area, per unit time, per unit frequency, and per unit solid angle. So we divide by dA. So this whole quantity here has units of specific intensity. And so this is the additional specific intensity. It just works out to be epsilon times ds. Again, that's a very simple equation to solve. The amount of specific intensity, there's just an addition of specific intensity of epsilon times S minus S naught. So that's pretty simple. Actually, I'm sorry, I must note that there must be a plus sign here. So I of S is I of S naught plus epsilon times S minus S naught. I'm going to correct that when I post it. So that's emission of radiation. And we are basically ready to talk about the equation of radiative transfer. And we're basically asking, okay, now let's put the two together. What happens if you have a medium which is both absorbing and emitting? That's very simple. You just put the two concepts together. The amount of change in specific intensity is going to be equal to, this is the absorption term. Notice that it's a fractional term because it has an I there. And this is the emission term. And this is just an additive term. It's not a multiplicative term. And so you can write it in a differential equation form. You get di by ds is minus alpha I plus E. That's a simple differential equation. Oftentimes, you're going to see the same equation cast in terms of what is called the optical depth. So the optical depth is just alpha times ds. Okay, so alpha is the absorption coefficient. It has units of per unit length per centimeter. And ds has units of centimeter, and so optical depth is dimensionless. Okay, so the optical depth kind of tells you what fraction of photons will actually escape. So it's a dimensionless quantity. So di by d tau is now minus I plus epsilon by A. Another terminology, epsilon by A, which is the ratio of emission to absorption coefficient, is called the source function. Why is it called the source function? Because this quantity depends only on the medium, right? So epsilon and A are properties of the medium. So it kind of puts the equation in a nice form where you only have the properties of the medium in one term. This is the specific intensity which you're solving for, and this is the differential equation for it. I noticed another error, sorry. So it should be d tau here. Okay, so that's basically called the equation of radiative transfer. One important thing to note here is I haven't written the arguments of all of these functions, but they're implied. So for instance, the epsilon and alpha can change with distance along the ray. Okay, so we will come to some problems of that kind in class. Also notice that all of these quantities depend on frequency. They could be frequency dependent. And so I haven't explicitly written the arguments here, but just be aware that these things can depend on frequency. The properties of the medium can change with propagation distance. Yeah, and so that's basically how you account for absorption and emission. And that's how you put all of that together and you get the equation for radiative transfer.